we've got a transformer here. There's 1,000 turns on this side and 6,000 turns on this side. 3 volts RMS coming in, so it's AC voltage. We've got a resistor on that side. So the primary coil has 1,000 turns, the secondary coil has 6,000 turns. 3 volts, that is repeating everything we've got there across the primary coil. Alright, calculate the voltage across the resistor. So we just have to work out what's the voltage on the secondary coil. So the turns are 1,000 to 6,000. So it's a 1 to 6 step up transformer. Okay, because 1,000 to 6,000 is 1 to 6. So therefore, we have the 3 volts and we times it by 6 to get 18 volts in our secondary. So there's 18 volts here. Calculate the peak voltage across the resistor. So we've just worked out that we have 18 volts, and that is RMS. Okay, the RMS coming in, that's also RMS. To go from RMS to peak, we go 18 volts RMS times √2. And that calculation gives 25.5 volts. And now we need to work out the power dissipated in the resistor for 2 marks. We've got 3 power formulas. We've got P equals VI, we've got I squared R, and we've got V squared over R. In this case, we haven't yet worked out I. We could if we wanted, but we don't need to because we can just go straight for this guy here. Question is, do you use the RMS or the peak? You use the RMS. So P equals V squared over R equals 18 squared over, what's the resistance? 1200, which gives us 0.27 watts. Alright. Same circuit, but we've got a switch there. So the 3 volt battery, it's now DC, not an AC anymore, it's a DC. And we've got a switch. The students have been asked to observe the current in the resistor as it's closed. Before the switch is closed, there's no current. This doesn't surprise them. When the switch is closed, there's a very short pulse of current in the resistor, and when it remains closed, there's no longer any current. Explain why there's a short pulse in the current. That's something we need to explain. And there's another one we need to explain. Why there's no current in the resistor. No numbers are required, but you should refer to the relevant law of physics. Okay, so we have to name a law. You actually have to put the name in there. Alright, because this is DC, a transformer doesn't work in DC. There's got to be a changing flux. The old one worked because there was AC. We had the voltage here was changing, the current here was changing, so the field from this one was switching back and forth. That field that was switching back and forth meant that the flux through this guy was switching back and forth. And because the flux was changing, we were making electricity in this guy. The key is the change in flux, and that's from Faraday's law. So that's the law we have to say. So I'm going to start with that for my first point. So why don't we just go with Faraday's law. Faraday's law, it states that an EMF, and because we make a voltage, and because there's actually a loop here, that voltage with a resistance, that voltage will make a current. So, and in this case, a current is induced, then there's a change in flux. So I haven't explained really anything, I've just stated the law so far. Change in flux. So now I'm going to talk about how this change of flux answers these two questions. 1. Why is there a short pulse of current when the switch is closed? And 2. Why is there no current in the resistor as the switch remains closed using this change in flux? Alright, dot point 2. So as the switch is closed, there's a change in flux. There is a change in flux. They say as the switch is closed, there's a very short pulse of current. So there must have been a change in flux. There is a change in flux. And where does this change in flux come from? Flux for a short time as the field in the left coil, this guy here, as the field in the left coil goes from 0 to, why don't we just call it on. Okay, so switch is open, no field, close the switch, it powers up, in a very short pulse to its full field that it's going to make as the current flows through, and it makes a field in that solenoid. As the current goes from 0 to on, so there we go, we've got the switch is closed, there's a change in flux for a short time as the field from the left coil goes from 0 to on. And what do we say, just to make sure here, in the right coil. So there's a change in flux in the right coil for a short time as the field in the left coil goes from 0 to on. Cool. And then we answer the second one, why is there no current as the switch remains closed? When switch remains closed, the field from the left solenoid so the field from this guy, which goes through and propagates through to him, but it's caused by the left solenoid, the field from the left solenoid remains constant, it stays the same. And because it's constant, there's no change in flux in the other one. Therefore, no change in flux in the right coil or the right solenoid. So let's just go over that one more time. We've got Faraday's law states that an EMF, and in this case a current, is induced when there is a change in flux. Right, so there will be a change in flux in this guy when the field from this guy is changing. So as the switch is closed, there is a change in flux in the right coil for a short time as the field in the left coil goes from 0 to on. And then when that switch remains closed, the field from the left solenoid just remains the same, and therefore there's no change in flux in the right solenoid.